Right, so we're going to start this module, CO650, by reminding ourselves about the basics of programming. And so in this presentation, we're going to talk about the main function, we're going to talk about input and output, different ways of commenting, we can talk about variables, different types, their memory addresses, and how we point to them and refer to them. We'll also talk about the scope of variables, local and global scope, talk about some operators, as well as casting between different data types, and then talk a little bit about time and how we can measure the number of seconds that have elapsed during our programs. And this is going to build into some of the exercises that we're going to do throughout this module. And just before we dive in, I'd just like to let you know about the formatting of the slides. And what you see in the light green boxes is pseudocode. So this isn't quite the complete code, but it gives you a rough idea, a rough design for what the actual syntax will look like. Okay, and that's what you're going to see in the light blue boxes. That's going to contain the actual C++ syntax that we're going to use in our examples and in the exercises for this module. And so without further ado, let's dive in and have a look at our first topic, which is going to be the main function. And if you have any previous experience with programming or any previous exposure to it, you'll be familiar that the main function is typically the starting place of applications. You'll find this in C#, you'll find this in Java, even Python has a main function, and in C++ this is no different. Interestingly, the C++ main function doesn't have to be placed within a class, which it does in C# and Java. In those languages, you'd be expected to declare a static class. In C#, it's a program, and I think it's also the same in Java. And within that, the main method in those cases is actually declared to be static, so that the compiler doesn't need to create an object of that class in order to be able to access and call the main method in that case. But here in C++, we don't have to put it within a class. It can actually exist independently. Typically going to be in the CPP file that's been created by Visual Studio or any other environment that you're using as a template, and that will create the main function for you. There's actually a few differences as well between the signature of the main function here, because in C++, the return type has to be specified as int. The compiler is going to expect an integer to be returned, and that's typically 0, which this wouldn't be the case in C# or in Java. That would just be declared as a void return type, and therefore no return statement. But here in C++, we need to declare the return type of this main function to be int. And you'll notice actually in the top blue box, there's actually a complicated parameter list. There's two parameters. The first one's referring to the number of arguments, and then the second one is a pointer to an array of arguments. And you might also see this in other languages like C# or Java as string args. So that's just a string array full of arguments which could be passed to this main function, and it's also the case here with C++. But it should be said, of course, that we're not going to be referring to this argument list, so we can actually do without it. You'll notice in the second blue box here that we've actually got no parameters within the main function. Okay, so we can do, as I say, that's perfectly fine for the exercises that we're going to be working with. All right, the only thing we really need to pay attention to is the integer return type. And of course, returning 0. If we try and return anything other than 0, that's going to provoke an error. All right, so make sure that you're returning 0, and importantly, make sure that this return statement is going to be the last statement in the function, because if it's first or in the middle of the function, it's going to terminate the function prematurely, and if you've got code underneath that return statement, that's not going to be executed. So remember that the order of statements still matters. It executes the statements in order that they're written, so make sure that you write them in that order. And of course, the purpose of the main function is the same as the other languages. It's the starting point of the application. So it's typically where we're going to instantiate objects of other classes and then call their methods in order to run and perform certain tasks. Okay, and then once we've performed all those tasks and we've finished the application, that's when we can return 0 to exit that application. And you're probably familiar with Visual Studio by now, but just to remind you that there are two different ways of executing your code. And that's through the debug menu, and you have the option to choose with debugging or without debugging. If you choose the debugging option, then it's going to run your code, but it's not going to pause on completion. So it'll actually exit automatically after the application is finished, and you won't see the final output or the final results of the application. It won't hang around. Because remember, of course, that the process of debugging is to remove the bugs. And so if your program runs without any bugs, then it's fulfilled its purpose. It's only interested in seeing whether your application can run from start to finish without any bugs. All right. So if it does that, it does its task, but you don't get to see the final result. So to avoid this, you can run without debugging. Okay, of course, the compiler is still going to check to see whether your program's syntactically correct, and assuming that you don't encounter any exceptions that cause the program to crash in any way, then you should see the final output and the information displayed on the screen, and it should pause. It should come up with the press any key to continue statement, which is essentially like an input, and it's going to pause the execution of the program until you type something in, and then at that point it then exits. Or alternatively, to running without debugging, if you do want to run with debugging to make use of all the exception handling mechanisms and the breakpoints, should you want to analyze any problems in your code, then you can do so and also maintain the final output at the end by including a system pause statement just before your final return 0 statement in your main function. Okay, so there's different configurations there depending on what process that you need to use, whether you're trying to handle and debug your exceptions or whether you just want to see the final output on the screen. There's lots of different ways to do that. Okay, so let's talk about hash include. And remember that the purpose of the main function is to utilize the functions of other classes. So we create objects of those classes and then call the methods. But these classes tend to be located in different files. There's a few differences between C# and Java in comparison to C++, because in C# and Java you tend to only create one class per file, and in C++ technically you can have multiple classes in the same file. And of course in C++ we have the header file and the CPP file. We're going to look at the differences between header files and CPP files in due course. But the main point that I wanted to get to was that, of course, we need to get access to the code in these files. The classes that are created in these files, we need to be able to access their functions. So therefore, how we do that in C++ is we have an include statement, typically at the top of the file. And this is actually something that's known as a preprocessor directive. Again, we're going to explore this in more detail in this module at a later stage. But for now, just know that it's an example of a preprocessor directive. You can tell these because they'll have a hash in front of the keyword, but there's a distinction we need to make between the syntax for including classes and libraries that are core to C++ and that are located within the IDE, and classes that we've created. Okay, because there's going to be a slightly different syntax for both of those classes. So if we're including classes that are core to C++, we need to use the angled brackets, okay, the greater than and the less than operators as we know them in comparisons. But here, just include those angle brackets to refer to the name of the library. And you'll see underneath that we're using a pair of speech marks like we would for strings to link to a file that we've created. Okay, and usually if it's included in the same directory as your CPP file, you wouldn't need to include the directory before that. So it would just be the name of the file. But of course, if it's located in a different folder to the main CPP file, then you would need to include maybe the level before that, or the folder that it resides in, and then slash the name of the file. Okay, so just remember that distinction there. If you're referring to C++ libraries and system classes, then make sure you use the angle brackets. But if you're referring to your own classes that you've created within a project, use the speech marks. And as we were just talking about the difference between header files and CPP files, you should be aware that in your main CPP, where your main function is going to be, you only need to include a link to the header files of classes that you've created. You don't actually need an explicit link to the CPP file of that class, because if you've used the GUI and Visual Studio to create a class and you've defined the name for your header and your CPP, it should be the same. That will automatically place a include statement in your header file of the class to the CPP file of the class. So going back to the main file, if you include a link to the header file of the new class, that in turn also contains a link to the CPP file of that class. So through the header, you get access to the CPP. Okay, so you don't need to have an explicit link to the CPP file. All right, and it's also worth saying that the semicolon is optional. You don't need to include that. You typically don't see that, but even if you were to add one, hopefully it shouldn't make any difference there to the compilation of the program. Okay, let's talk about namespaces now. And you'll see here in the blue box that we've actually set up two different namespaces that have different names, so they're arbitrary names in this case, my first namespace and my second namespace, but notice that they actually contain the same integer variable labeled A and have different values. So this is an example where you may want to indicate different regions of code which have similar names of attributes. Perhaps they even have similar function names as well, if they're all typical operations like insert and display and add and remove, etc. Okay, that can be distinguished. You can differentiate between them by the name of the namespace. And looking at the main function here, we see that we refer to the individual variables, A in this case, through the namespace. So you'll notice in that first line, int c equals my namespace : A. And that : is technically known as the scope resolution operator. This is how we can directly refer to variables or even methods of a particular structure or class. Okay, and that's how we differentiate between the two variables of the two namespaces. And then you'll notice in the third line that we actually use the keyword using there. And this effectively means that we don't have to then refer to the namespace every single time we want to refer to that particular variable. So you notice in the line underneath, c equals A plus my second namespace : A. That A is referring to the A from the first namespace. Effectively, as we are using it, we don't then need to repeat that that's where A is located. Okay, we've kind of identified that this is the designated namespace that's going to be adopted. Therefore, we can avoid prefixing all of the attributes and functions within that namespace and just refer to them directly. Okay, and of course, whilst we're not going to be making extensive use of namespaces in this module, of course, we will be using and referring to things from the standard library, which is abbreviated to std. So you'll probably notice in most of the exercises that we do, we're going to have a using namespace std statement above our main function. And of course, this saves us having to prefix all of the input, cin and output, cout statements with std. We can just refer to cin and cout without having to write std constantly. Okay, so it just saves us a lot of writing really in our code. Okay, and so this is going to be the main reference and the main way that we're going to be using namespaces in this module. But of course, should you want to use them, they can be very useful, certainly in identifying and organizing your code. So if you've got a lot of different files, you may want to place them in separate folders, and it might be a nice way to organize your files that way. Okay, especially if you're going to be reusing code or you're going to have similar code between lots of files. So useful for avoiding naming conflicts. Next, just a brief reminder about comments. Again, if you have any previous programming experience in Java or C# or even C++, you'll know the format for single line comments, which are of course 2 forward slashes, and hopefully you know that comments are not going to be interpreted by the compiler. They're just a useful way that we can write notes to the reader of the code, just to explain things which may not be obvious. If it's a complicated line of code, it's useful to just write a note to explain that, or a particular reason why it's included. If it's obvious, then obviously you don't need to include lines of comments for that, but if perhaps it's not so obvious, that's when it's appropriate to write a single line comment. And likewise, group comments are also following the same syntax as Java and C#, so that's going to be / to start a block comment, and then once you've finished that comment, it's going to be * to end that block comment. This can be quite useful for including summary comments above methods. That's a good documentation feature there. If you write a summary of what the method or what the function is going to do, that's going to be useful for the reader. Or perhaps if you're having problems with the syntax, you can also comment out a block of code to allow the application to compile so that you can test up until that point. And also, it should be said that in Visual Studio, you can also highlight a block of code to comment out. Saves you having to write all these symbols yourselves. So I think that's in the Edit menu. You can go down there in the Edit menu, and I think it's in the Advanced sub menu that you can then select to comment or uncomment the highlighted selection of code. Okay, so do include comments where they're relevant and where they're appropriate. So they're useful notes to the reader and good documentation practice. Next, let's remind ourselves about how we output data to the screen. And in C++, this is using cout. And you might think that cout is a function or a command, but actually it's an object of the output stream class, or otherwise known as the OStream class for short. And this is located in the standard library of C++. So we could actually write using namespace std above the main function here in the blue box on this slide. Or if you don't do that, you're going to need to write std scope resolution operator, which are the 2 colons, and then cout from there, because it resides within that standard library. And so regardless of whether you use the namespace std or you don't, you're going to need to have the 2 angle brackets are following that. And this has actually got a particular name. This is called the insertion operator. And you'll notice that in this example, we've actually declared a variable in the line above. It's an integer variable with the value of 10. And we then just pass that to the cout object, which then connects with the command line application, the console application, and then displays that on it. Okay, so notice here that the variable actually points towards the angle brackets. The insertion operator actually points towards the cout object, and in a minute we're going to see that the cin is actually the opposite way around, so it actually points towards the variable. Okay, and let's do that now. So cin, the opposite, of course, is input. So this is where we connect with the input stream, the iStream class. And of course, we're going to need to connect the software level, the compiler level, with the actual physical level, the keyboard, so that we can actually type data in on the keyboard, and that's then passed through the layers to the software level. Okay, and this input stream is how we facilitate that. Okay, and so here in this example, we are actually using namespace std this time. You can see that. And so therefore we don't need to write std before cin. We can actually just say cin and then point towards the, using the extraction operator. These are the angle brackets pointing the other way. Okay. And it points towards the variable that you actually want to store the data in from the keyboard. And the useful thing about C++ is that we don't have to worry about converting between data types. So in other languages, like C#, for example, when you use console.readline, that actually returns a string. So if we want to actually input numbers, we have to then convert that to an integer. But notice here, with cin, we can input directly as an integer. So if we type a number in on the keyboard, that's going to be stored in the corresponding data type to the variable that we're storing in. Had we set it up as a string, of course, that number would be stored as a string version. But as C in this case is an integer, it's going to be stored as an integer. All right, and then of course in the line underneath it, we're just printing it back out to screen. Okay, so as you can see there, cin points towards the storage location, the particular variable that you want to store what you type in on the keyboard, and then for cout, that data then has to point towards the cout object in order to print it to screen. Okay, and the end L is short for end line, and that actually just flushes out the buffer, the stream, the connection between the layers. Okay, so there we go. That's just a quick recap on output and inputs. Okay, so let's move on now and have a look at variables and the associated data types. And so hopefully this is familiar to you if you have previous programming experience. Hopefully you'll know that in order to declare a variable, you have to have a data type followed by an identifier, or otherwise known as the variable name. All right, and of course, this is how we can store data in our programs. So it's useful for storing values that we can later refer to or modify in some way. And when it comes to choosing variable names, we have to follow a few rules. For example, we can't start with digits. We can only start with a letter or an underscore. It is possible to have digits within the variable, but we just can't start with them. All right, but it's usually good practice to begin with a letter, and if we're going to have more than one word as well, we can't use spaces. So you either have to separate the words with an underscore, or you might use camel casing, which of course is where you make the first letter of the new word uppercase, and then the following letters to be lowercase. This is helpful for differentiating between the different words, makes it easier to read. And it can't be a reserved word, all right? So it can't be a keyword like public or const or class, or another type of data structure as well that may be defined within the standard library. Okay, so make sure your variables are unique, and it's always best to choose meaningful names. So of course you've got the syntactic rules, which we just mentioned, but of course logically it's going to make your program much easier to read and for other people reading it as well if you choose meaningful and appropriate variable names. All right, so make sure they're relevant and specific to what you're storing. All right, and of course the names that you choose are case sensitive as well. So just like strings, where it's possible to have the same word in a string but with different casing, they mean the same word, obviously, and we know they are as humans, but the computer treats them as separate literal strings. And so it's the same with variable names as well. You might have the same variable name, but with different casing, and of course that is treated to be different. All right, so just remember that. Hopefully you can avoid using similarly named variable names if you choose them to be specific and you're not using unnecessary variables. All right, so if you've designed your program well and you're only using enough variables that you need, then hopefully this isn't going to be a problem of having lots of duplicate names, but just be aware of that in case there are any exceptions. All right, so that's the variable names, the second part of the statement. Let's talk about the first part of the statement, which is the data type. Okay, and as C++ is a strongly typed language, we need to choose a data type that's appropriate to the data that we're aiming to store in this variable. We can't mix and match as we go. Okay, hopefully you know this. But just to reiterate that we have lots of standard primitive data types, such as char, stands for character, a single character, and of course that is one of the smaller data types, as you can see here, 1 byte that only takes up a single byte in memory. So again, if useful to design your programs so that you're not using more memory than you need. So if you're only intending to store single letters, it's probably best to use a char rather than a string, because a string takes up more memory. And of course, you've got lots of other data types for storing numbers, such as integer. So that's for whole numbers. And judging by the range and the size of the data type, I think this is a 16-bit integer. Yes, because that's 2 times 8. That would give you 16 bits if it's 2 bytes. Yeah, and so that does have a limited range from the minus value to the positive value. Of course, if you're choosing an unsigned value, you can go higher than that. But of course, there are other data types such as long, which would be useful for much larger values that you intend to store. And of course, float, by contrast, has got a bigger range because it's a larger size. So that's got to be a 32-bit type, hence why the range is much larger. And the advantage of floats, of course, is that you can store decimal places. So if you're choosing to be very specific in your calculations, or perhaps you're trying to model currency, 2 decimal places, for example, float would be appropriate. Okay, and then of course the other small data type listed here is the Boolean data type, which, as you know, that's only going to store true or false. So that's useful for particular flags. If you want to check the status of something, you know, is this completed? Has this been checked? Does it pass a test? You can say whether that's true or false. And whilst we're talking about data types, we should also point out that it is possible to define aliases for data types in C++. And this is using a particular keyword called typedef, short for type definition. Okay, so here's where you can define a new name, a new alias for a particular data type, basically to then substitute that within your code. As you can see in the blue box here, we've defined a alias for integers as mark, meaning that in the second line we can then say mark as the data type rather than int. And whilst you may not see the point of this for standard data types like integer or float or char, because they're fairly short and self-descriptive, this can be useful for when you have longer function names. If, say, you're setting up function pointers, they can be quite long if they're quite specific. So this can help to shorten that and save you having to write it out every single time. And similarly for class names as well. Okay, so it should be said that this isn't creating a new type, but rather defining an alias, an alternative name for a particular type. Okay, so just let you know that's possible, and we're going to get into function pointers later in the module. Okay, so we'll talk more about that then. Let's move on now and talk about defining a variable. So technically there is a difference between definition and declaration. Declaration is where you would declare the variable, i.e. to say it exists. You would have to have the data type and the variable name, but definition is where you add meaning to that variable. That's where you actually assign a value and say that this is what this particular variable means. So they're pretty similar, but technically there is a difference, and often the two words get used interchangeably. Here we're using definition, even though we aren't specifying a value, but still the variables are being defined in terms of their data types and their variable names. Right, so now that we've distinguished between the two, here we see in the first blue box, we see 4 different definitions. We see different data types being used and different attributes of a person being defined. Again, the data types chosen are relative to the particular type of data that's being stored. So hopefully that's fairly self-descriptive here. If you were to look at the second blue box, you'd see that we can actually specifically declare integer variables to be signed or unsigned by using the keyword. And by default, integers are signed, so they can store minus values by default. So technically, you wouldn't need to specify the keyword signed in front of score, the definition of score here, the second line in the second blue box. This is probably going to be more appropriate when you need to declare a variable to be unsigned. So that's where you do need to specify that, so to override the default setting. Remember that the signed and unsigned, the sign there means positive or negative. So whether it's minus or minus value in front of it or a plus. We don't really tend to use the plus sign in front of positive values. It's probably only going to play a part for minus values where we have a minus, a dash sign in front of the value. So if we do need to have an unsigned integer where we don't want to have negative values and we want to use the memory attributed to the minus values, if you remember back to the range that goes from minus to positive, we can then duplicate that minus range in the positive range, basically doubling the range of positive values that we could use. Okay, so should you ever need to make use of that, you can do so by using the unsigned keyword. All right, and of course, finishing up here with the final blue box at the bottom, you can also define multiple variables of the same type within the same line. And here you'll notice we're using commas, saving us having to specify the data type every single time on separate lines. Okay, so that's just a shorthand way of doing that. And it's also common to assign a value to a variable when it's declared and when it's defined. And this has a special name. This is known as initialization, where you specify an initial value for the variable being defined. As you can see here, in the first blue box, we are defining the variables and we're also assigning default values to them. Okay, so we are initializing these variables. And so typically, you'll probably see values being assigned via the equal sign. We, of course, call this the assignment operator in programming. So it's not comparing to see if the two sides are equal like they are in maths. It's actually assigning the value on the right-hand side of the assignment operator to the left-hand storage location. All right, so hopefully you're familiar with this. And so that's typically what we'll see. But of course, alternatively, there's direct initialization syntax, otherwise known as implicit assignment in the second blue box, where you can actually specify brackets. So a little bit like parameters for a function, we're actually using those curly brackets here to specify the value within that, which is actually directly joined on to the variable name. Okay, as you see here. Next, let's talk about variable scope. And you'll see here that there are actually 3 different types of scope, 3 different levels of access to variables. And that has all to do with where they're defined within the context of a program. If you look at the first line in the blue box, int n1 has a value of 30, but notice that this is assigned outside of the function f and the main function as well, and it's declared above those 2 functions, more importantly, meaning that it's then accessible to all of the code below its declaration. So function f can see it and the main function can see it. All right, it has access to it. Whereas if you look at the variable n3, which is declared within the f braces, the function f that is, that variable is only going to be local to that function, i.e. the main function wouldn't actually be able to see it because it's declared within the context of that function. Even though it's declared above the main function, it's only limited to the braces that it's been declared within. Okay, so if we wanted to get access to it, we'd actually have to pass it somehow to the main function. But this indicates local scope, and this will apply to all of your other functions and within your other classes as well. So that's the difference between global scope, which is visible to all of the code below it if it's declared outside of the context of a function, whereas variables that are declared within a function will only be accessible and visible to that function. And this is because the memory for that variable is actually deleted when the function terminates. And whilst C++ differs from the other languages in other contexts, because it does actually have manual memory management for other constructs such as pointers and objects, there are points where we can actually define that we want to delete those at particular points. We're going to explore this a little bit later on in the module. But C++ is like the other languages in that it does automatically delete and free up the memory for standard primitive types at the end of functions. That's the automatic memory management, okay, like your other languages. So you don't need to worry about that. So just know that those variables declared in the context of functions are only visible for the duration of that function. And finally, there's one last scope which we need to mention, which is static scope, or otherwise known as file scope. And here, in this case, because we're in the main file, the main CPP, where the main is specified, this static variable, in this case, is going to be visible a little bit like a global variable, really, because you notice we can also refer to it within the main function. But in the context of classes, that means that we don't actually have to create an object of a class in order to be able to access this static variable. If this, say, was located in a separate class, I could refer to this static variable through the class name. I don't actually have to create an object of it to be able to access it. And that's the same with methods and functions as well. Static functions also can be referred to through the class name and not the object name. Let's talk about the string data type now. And C++ is actually similar to Java with strings in that it declares the string data type as a class. Okay, so it's actually not a standard primitive type. It's a complex type as built as a class, meaning that it has attributes and it also has functions, which are quite useful, of course, for accessing and learning parts about the string and also splitting it up and dividing it and returning substrings. So lots of useful functionality there that you can use within your programs. But this is actually located in the standard library. Okay, so you can get access to this by just using the namespace std, and that will grant you access to the string class, meaning that you can then set up string variables. But where C++ differs to Java is that C++ actually specifies the string class with a lowercase s, and Java specifies it with an uppercase s. And that's mainly due to the naming convention of Java, in which specifies that all classes have to have an uppercase letter to start with. But in C++, know that string is going to be a lowercase s at the start, but it does have class properties and functions. Okay, so you would use that as a normal data type in front of a variable, an identifier name, and of course you can then assign it values, and then all those values have to have a speech mark before the value and then after the value. Okay, so here in this case we're just assigning a name. You can take spaces, of course, and that is then stored as a string. And again, just to remind you, you're probably familiar with this, but a string is actually an array of characters, so that each one of those characters of a string is stored as a separate element in an array. Okay, so you can actually get access to particular elements and particular letters within a string by referring to the index of that array. And so here in the second box, we're actually referring to the string name array declared in the first box. But if you refer to the element 0, which is going to be G in this case, uppercase G, you can then store that separately in a character variable. Okay, so very useful ways of getting access to parts of strings, and useful for searching. Again, we're going to look more at that throughout this module, and indeed in the follow-on module as well in CO658, data structures and algorithms. So this is all very useful information. And again, we mentioned earlier about different functions being defined in the string class. Just one of those useful functions is the length member function, which will return how many characters are part of a string. Okay, so if you need to know the size of a string, you can get that by just calling the length function as part of your string variable. Okay, so the string variable actually acts a little bit like an object, so you can use the dot notation there. It would be the object name dot function name. Okay, so you'll see here it's name dot length, and as it's a function, of course, has a pair of brackets. Okay, and then that returns an integer, which we can then store separately in number chars. Okay, so that's the string type. Let's move on and have a look at constants. So again, you should be familiar that we can declare variables to be constant, meaning that their values should never change from the first value that they're assigned. So it's really important that you initialize constant variables with a value to start with. And if you see here in the second blue box, we have to specify that a variable is going to have a constant value. And you do that by having the keyword const prefixing the data type. And that goes without saying that, of course, you do need to declare what data type it is. The const keyword doesn't replace that. It simply goes before the data type. And then you'll notice that the variable name is actually all in uppercase. And this is a typical convention across most of the languages, just to differentiate between constant variables and variables which, of course, have changing values, which are in a mixture of uppercase and lowercase. Okay, so this just makes constant variables stand out from other variables. So in this example, we're representing retirement age, which of course may change in years to come, but at the time of writing this slide, it was 65, and so that value is assigned to the constant variable, and then of course all the references to this variable will refer to that value. Okay, so constants can be really useful for values which will stay the same throughout the duration of the program. And this is one example of it. There are, of course, many other examples that you could use. One that comes to mind is actually setting up a constant variable for the size of an array, where you indicate how many elements are going to be within a fixed length array. And then, of course, this saves you having to write out that array size in all of your iterative statements, okay? And of course, the advantage of that would mean that you only have to specify the array size once. And should you then want to change it, perhaps for testing purposes, if you don't want to have to put in 50 different values every single time, you may only want to test it for a few values. So you can change the size of the array to make it much more manageable. And of course, this saves you having to update all of your iterative statements, where you'd have to specify how many times you want to repeat. You can, of course, refer to your constant for the array size rather than a hard-coded number of elements. Let's talk about the memory addresses of variables now. And of course, we refer to variables via their name, but for the values to actually be stored somewhere that they can later be referred to, this has to be stored in a location on the computer's memory. Typically the RAM, of course, and there's a difference between memory allocated to the stack and memory allocated to the heap. We're going to explore that later on in the module, but just know for now that the computer's memory consists of memory cells, and it's in these cells that the values for our variables and even objects as well are stored. And the name of the variable actually is an alias for the memory address. Okay, it's much easier for us to refer to the name of the variable rather than referring to the memory address, as we may not know it unless we've printed it out. But at that particular memory address on the computer's RAM is stored the value of the variable as well as the variable name. Okay, so there's actually two different things that are being stored at that memory address for primitive type variables, that is. And each memory cell is given a unique address. And so if you were to print this out to the screen, as you see in the blue box, the comment shows a typical output that you would see. It's typically a hexadecimal address with letters and numbers there. And the cells are actually given consecutive addresses. So if you were to create an array on the memory, you would actually be allocating a block of consecutive addresses. And if you were to print this out to screen, you would see those numbers increasing by the size of the data type. So if that's integers, they should increase by 2 each time because they're 2 bytes. Likewise, if it's float, they'll increase by 4 bytes. So you'll see the numbers change, basically, okay, of the memory addresses. And of course, the key thing here, which we need to mention, is how to actually print the memory address to the screen. And you can get to the memory address by using the reference operator, which is the ampersand sign. So you've probably used 2 ampersands when referring to the AND operator for conditions, where you want to evaluate 2 or more conditions. You would join them with an AND operator, the 2 ampersands. But a single ampersand sign placed before a variable will actually refer to the memory address of that variable. Okay, and you can see that's what's being printed out here in the cout statement. Okay, so therefore, if this was to run, that should print out the hexadecimal address to the screen. And then you can actually define special variables that can point towards the memory addresses of other variables. Okay, and these are called pointers because they do just that. They don't contain values of themselves. The value that they do store is the memory address of another variable which holds a particular value. And so there's a particular format for defining a pointer variable. You have to specify the data type of the particular variable that you're pointing towards. So if you want to point towards an integer variable, then your pointer variable also has to be an integer. And then you have to include the asterisk symbol. And despite C++ being a strongly typed language, it's actually pretty relaxed when it comes to the placement of this asterisk. As you can see in the green boxes, it can go immediately after the type, or it can go immediately before the pointer name, or it can go in the middle of both of them with a space in between. So it's pretty relaxed. The asterisk just has to go somewhere in between the type and the pointer name. And so once you've defined a pointer variable, and you'll notice that it's also good practice to initialize it to be 0, assuming it doesn't conflict with the 0 memory address. It's unlikely that it will. So you can go ahead and assign it to be 0, just so it's initialized. But then if you cast your eye to the blue box here, which contains a code snippet, you'll see in the second line that we've defined a pointer. You'll notice it's an integer pointer. It's got an asterisk there, and it's got a name of pointer to age, which is aiming to point towards the age variable, which is actually declared in the line above, the first line. But back to the second line, we then assign that 0, as we said, good practice. But then in the third line, notice that the pointer is then assigned the reference of the original variable, the age variable. Okay, the non-pointer, the standard integer variable, age. We wouldn't be able to assign it the value of age, the integer value of 21, because the only values that a pointer can store are memory addresses. So that's a hexadecimal address. It's not technically an integer. So we can't store the value of age, but we can store, and the reason why we've set it up, of course, is to store the reference, the memory address of that particular variable. So hence you'll see that we're using the ampersand sign, as we saw in the previous slides, to refer to the memory address of that age variable. And then when it comes to printing out that memory address stored in the pointer, we don't need to use the reference operator, the ampersand, because we've actually stored that memory address. That is the value of the pointer. Okay, so we don't need to use the ampersand. We just state the pointer name to print it to the screen. Okay, and should it be the case that we actually need to see the value of the original variable, we can actually use the dereference operator, which is the asterisk. And you'll notice that this is actually the same asterisk symbol that we used to set up the pointer in the first place. So it's actually being used twice here, which can be confusing to some. Okay, so just be aware that it's used in two locations. And if you have a look at the blue box here, which contains the code, it's the same code as the previous slide, but we've modified the cout statement rather than just the pointer name, which would have displayed the memory address of the original variable. We've actually included the asterisk in front of the pointer name, which will then refer to the value stored at that memory address, which is the original variable, which has the value of 21. So that's what we'll actually see printed to the screen. Okay, and here on the next slide, we've got a diagram to help us out in visualizing how a pointer will point towards the details of a nav variable. You'll see in the table above that we've got 4 variables declared on memory. And you see the address, the data type, the identifier name, and the value that they store. And if you have a look at the value of the last variable, which is a pointer, you'll see it in the type. It's int asterisk. It's got a identifier of ph, short for pointer of age. And notice the value is the memory address, 1000 in this case, of the variable for age, which has the address of 1000. Okay, so there you go. There's a visual aid there to help your understanding of pointers. It's quite an abstract subject. I do appreciate that. So hopefully this visualization will help. And again, we've got another example where if you have a look at the blue box here, in the last line, we're printing out the address of age with the reference operator, the ampersand sign. So that will display the memory address of that particular variable, which is 1000. It's the first variable, the age. And then we display the value of ph, the pointer, which in the line above we set up to hold the memory address of age. Okay, so we don't have to include the reference operator. We just see the actual memory address because that is the value of the pointer. So that's another 1000 being printed to screen. And then in the final part of that cout statement, we actually dereference the pointer. So remember, we mentioned previously that this will actually get the value stored at that particular memory address. And of course, because ph holds the address of age, the value stored at age is 21. Okay, so if you look at the comments, you'll see a confirmation there that we see the memory addresses, 1000 and 1000, there should be the same. And then the value for the original age variable, which is 21. And finally, just before we move on from the concepts of memory addresses and pointing towards them, I should also mention that it is possible to set up an alias for another variable, a way to directly reference and refer to the memory address of another variable. You may be familiar with parameter parsing and passing by reference. That's what happens there, where you actually pass the memory address in to a parameter of another function, and that parameter is basically an alias for the original variable. It holds the memory address of that original variable, and therefore within the function you can directly access and modify the value for that particular memory address. And so the syntax for declaring that alias in the parameters is actually going to be the same to declare a reference variable outside of the parameter list of a function, which you'll see in the blue box here, where you actually have a reference operator after the data type for a reference variable. Okay, so in the first line of the blue box, you set up a character variable, and then in the second line, there is a reference, as we said previously, which has the reference operator, which refers directly to the first variable. And then in the third line, you can then set a value for that reference variable, and that will directly modify the value for the first variable, the variable to which it refers to. Okay, so that's just another way that you can directly refer to the memory address of another variable. Okay, so now that we've had quite a comprehensive recap on pointers, memory addresses, and references, let's change subject and talk about different operators. Hopefully, most of these will be familiar to you if you have previous programming experience, but just to quickly remind you of them, the equal sign is the assignment operator, and hopefully you'll know that the assignment operator will assign a value on the right-hand side, the R value, to the storage location on the left, otherwise known as the L value. Okay, and then of course we have all of the typical mathematical operators, the division, which is /, minus, plus, and asterisk. The asterisk, of course, is multiplication. We don't write x, we write asterisk to multiply different values or variables together. Okay, modulus sign is the percentage sign, and this of course will give you the remainder of a division rather than a number of times that a divisor will go into the dividend, i.e. how many times 5 will go into 50, for example. And this can be quite useful for when you want to repeat code in a particular pattern. So if you're dividing a number by 2, that will always go perfectly into an even number, therefore giving you a remainder of 0. Or if you try and divide an odd number by 2, that will give you 1. Okay, and therefore you will always have a remainder of either 0 or 1, and it will alternate between the two. So if you have code that needs to alternate, then modulus is a good way to achieve that. Okay, let's move on. Decrement and increment operators. So hopefully you know this is shorthand for either increasing a value of a variable by 1, that's the increment operator, ++, typically used in iterative structures where you have a counter and you want to increase that by 1 for every iteration of a loop. And likewise, you can decrement, where you decrease the value of a variable by 1. That's the minus. Okay. You can also do compound arithmetic. So rather than having to say variable equals variable plus value, you can then say variable plus equals value to actually add the particular value to the current total or the current value of a variable, rather than overwriting that, of course. And then that format, of course, applies to all the other mathematical operators for multiplication, division, and subtraction. Okay, what you may perhaps not be familiar with is the difference between prefix and postfix. And I'm guessing you're probably more familiar with postfix, as that's the conventional format for incrementing a value. You know, think of your loop counter, what we mentioned earlier. If you have I++, that's a postfix example. However, prefix would be actually saying ++i, meaning that you actually increment the value in prefix before then assigning it. And if you have a look at the example given here, you'll see the line first value equals ++ second value. That's an example of prefix where you increment the value. Say second value has the value of 5, then 5 will be incremented to 6 and then assigned to first value. It's actually the other way around. You assign the value to first value and then increase that. And even though the result will be the same in this example, where the result will always be 6 if the values were first 5 and then incremented, the difference between them is the order in which those operations are conducted. Because remember, prefix is where you increment and then assign, But in postfix, you assign and then increment. So if that order is important, perhaps in another scenario, something might take place in between those two operations, then the timing and the order of those operations, whether you increment and then you assign, or whether you assign and then you increment, may actually affect the result in that case. So this is definitely something to bear in mind when you're trying to write your code efficiently. Don't forget about the order in which operations take place. But just to finish up with our recap of operators, the final bullet point here mentions the relational and equality operators. So hopefully again this is familiar to you. The two equals signs are comparison, and of course this will check to see whether the left value is the same as the right value. Different from the one equal sign, of course, which is assignment, and that assigns the right hand value to the left hand value. Okay, and then you've got the not operator here, which is exclamation mark equals, checks to see if the left hand and the right hand are not equal. Okay, and then you've got greater than and greater than or equal to, and likewise less than and less than or equal to. Okay, so hopefully that is a quick recap of some of the key operators that we're going to be using in the module. Let's finish up this presentation by looking at time. And, you know, I appreciate it's been a long presentation, a very comprehensive recap. But this slide about time is going to be important because actually it's going to build into your assignment for this module. Okay, so I know it's been a long presentation, but make sure you pay attention to these slides here regarding time. And if you wanted to calculate how many seconds it takes for an application to run, or perhaps in the context of an assignment, you want to update something every second, then you can harness some of the attributes and functionality of the time class. That's core to the IDE. It's actually time.h that we have to include in our projects to be able to access this functionality. But within there's actually a variable that holds the number of seconds that have elapsed since January the 1st, 1970. So as that's over 50 years ago, that's going to be quite a lot of seconds. Okay, but thankfully there is some functionality within this class that can convert that number of seconds into a format that's more accessible to us, whether that's a calendar date, such as a date in the year, or whether that's a particular time of day, 24-hour clock, 12-hour clock, etc., etc. Okay, and this is also going to be important whether we want to measure the number of seconds that have elapsed since running a program, because we want to take a snapshot of time when we start the program or start an operation, and then take another snapshot when we finish the application, and then minus one from the other to get the number of seconds that have taken the application to run. Or in the case of the assignment, where we want to display an update every second, then we want to keep harnessing the number of seconds and get the date and the time and keep printing that to the screen on every interval update, whether that's every second or every minute or every hour. Okay, so let's have a look at some of the code that's required to actually do this. Okay, so looking at the explanation here, we see that we need to include time.h, so that's going to be at the top of the file. And then the time date is stored in a variable of type _time32_t. So this is a variable that exists within the class time, and then there's actually an _time32 function, which will populate that particular variable, passed in as a parameter, with the current system time. Okay, the number of seconds, all right? And those number of seconds are then passed to the _localtime32_s function, which then populates the tm structure, short for time, with the appropriate intervals, and whether that's the number of seconds, hours, days, month, and year values. Okay, so we can then access those particular intervals by using the dereference operator, which is the arrow. Okay, and then to display the time as a string, pass that TM structure to the ASCII time underscore S function in a character array, which is then populated with the time as a textual description. Okay, which we see done in the code here. All right, so don't worry if you don't understand quite all the formats and the function names, but just include code similar to this. I think it's going to be one of the exercises that we're going to get to anyway in this week. So make sure you have a good attempt at this. As I said, this is going to be important for the assignment, so don't neglect this. Have a go, make sure you can get it working, because this time functionality is going to be powerful to harness both in this application for your assignment and for future applications. Okay, so in fact, I think we've reached the last slide here. Yes, so I'll tell you what, here's a good time to then transition into having a go at some of these exercises. Okay, and I'm going to walk through a few of them for you and then ask you to have a go at the rest of them. Okay, so I'll get you started with the first ones. Okay, so I've loaded up a new C++ console project here. You can see on the right-hand side of my screen. I've got the exercises on the left-hand side of the screen just for easy reference, so I can look and see what we're doing here. But on the right-hand side, I've got my Visual Studio with a new C++ project, and you'll see here we're given a CPP file to start with. I've just named mine after the module and the week that we're on. But you see, we've got the CPP, and we've also been given the main function already. It's given to us as default, as part of the default template. Okay, so that's rather helpful. We've also got a few comments given to us as well, just in case you're struggling to find your way around. Maybe if you're new to Visual Studio, this might be useful for you to have a read through. So it's really good at helping us to get going if we're new with Visual Studio and running projects. And we've actually already been given an output statement, which is the good old hello world example. So if you were to read any books on C++ or any language for that matter, you'll see this is a very common exercise just to test that you can get something printed to the screen. Okay, and you remember we looked at outputs within the presentation. You remember that in C++, the cout is an object of the output stream. It's part of the standard library, so that's why we've got the scope resolution operator here. And it allows us to print things to the screen. And if I was to run this, lots of different options, remember from the presentation. I'm just going to press Ctrl F5 to run without debugging for now. And if you to run this, hopefully you would see hello world printed to the screen. Okay, so we're in a really good place to start with. We can simplify this a little bit. Remember what we said, rather than having to constantly refer to std, if we use that as the namespace, so just above main, I'm going to write using namespace std, and then I can actually delete the prefix to cout. If I run this again, you should see exactly the same results. It just allows me to refer to cout and cin without having to prefix it with std all the time. Okay, so it's just easier, I find, to use the namespace. All right, as given here. Okay, and we should have already included the input and output stream. That should have been given to us, allowing us to, of course, refer to cout. So we actually should have everything we need to be able to have a go at the first exercise. So if you were to just scroll down on your exercise document, you should see that we've got a very gentle exercise to start with. It just asks us to write some code for a user of an application to enter their name and their age, and for those details to be stored and then printed to the screen again. Okay, so we already know how to do outputs. We've just done it with cout, okay? And hopefully you remember that cin is C++'s version of input. So if I was to modify this, rather than printing out hello world, if I just modify the contents of that string, and let's say we ask for the name first. We say to our user, please enter your name. That's my output. That's going to be the request. But now I have to find a way to capture something from the keyboard. Okay, and so this is the second line where we write cin. All right, remember that cin points towards a storage location, a variable. I don't currently have one, so I should probably set one up then. And we're given the types that we're supposed to be using for our variables. So name is supposed to be a string type. So I'm just going to write string name there. Data type comes first, as always, and then the name of the variable. All right. And now that we've declared that, I should be able to input into name. Okay. And let's do the same while we're here. Let's do the same for age as well. So I'm going to set up a integer variable for age. It's just int, int for short for integer. And let's do a very similar process where we output a prompt to the screen and then wait for the details to be typed in. And then what we type in on the keyboard is going to be passed to the input stream, the object of it, the cin, and then that's going to be stored in the storage location, our variable, okay, which we specify. So we want to store the name that they type in on the keyboard into the name variable, and we want to store the age that they type in on the keyboard when prompted into the age variable. All right. And so if we were to run this as it is, it would work, but I wouldn't get any visual confirmation on the screen. So it might be useful to have one last cout statement, one last output statement, where we actually print the contents of those variables to the screen. So it helps act like a confirmation to the user that they've typed in the right details and they've been stored, just so we know. All right, so I'm going to construct a sentence here. I can say, hello. And then I'm going to, rather than the plus sign, if you've used other languages like Java and C#, it's concatenation when you actually join string data with variable data as the plus sign. But here we actually use the operator. So we're going to use the chevrons again. Okay, so it's not the plus, it's going to be the two chevrons, helping with the output stream, of course. And then we write the name of the variable we want to print the value for. Remember, if you include a reference to the variable, it's going to look at the value, unless you specifically tell it to look at the memory address by using the ampersand. But we want the actual value that's been stored there. All right, so hopefully this would read hello, and then space, of course, and then the value of the name, whatever I type in on the keyboard. And let's finish this off with a statement that you are, oops, and then also include a reference to age, and then say, actually what we'll do, we'll put that there as well. Okay, so let's just do a bit of formatting here. And let's give this a try. So I'm going to try running this and see what we see. Okay, so first prompt is for the name. Type in my name. Okay, and then my age. And then we see the confirmation because I'm actually joining the data from the variables with the actual sentence that I'm constructing. All right, so there we go. We see a confirmation. Okay, so hopefully you'll find that a reasonably gentle process to get started with a bit of practice for input and outputs. Okay, just to test that you're on board with that. I can't imagine you'll have any problems. But if you do, just review these steps here that we've shared, and hopefully you'll pick that process up in no time at all. But just while we're here, I just wanted to mention the difference between running with debugging and running without debugging. Because if you pay attention to this output here, you notice that we've got the compilation, which is the .exe. It's obviously worked okay, but then it's got this message to say, to automatically close the console when debugging stops. You can actually enable that by going to this menu. So if you remember what we said in the presentation, it seems that this version of Visual Studio 2019 I'm using has actually disabled that automatic exit upon the completion of the program, which was a problem in older versions of Visual Studio, but it seems to have been disabled by default in 2019. Okay, so hopefully, actually, you shouldn't have a problem with the differences between running with or without debugging using the default settings. Of course, you can turn that off, but just to illustrate, it shouldn't matter whether you run with or without debugging. For example, if I choose with debugging, where it should actually exit as soon as I finish the program, it doesn't. It actually waits for me to confirm that. All right, and I'll do what I've been doing before just to show you. Control F5 is without debugging, and you'll see exactly the same. Okay, so I mean, if by any chance you are using an older version of Visual Studio, we can still use system pause. That's a very helpful command actually in other circumstances. So that will come up with an additional statement that will say press any key to continue. All right, so let's run it again, and you'll see that happen twice. Okay, so there we go. There's the press any key to continue, which would have prevented the program from exiting had I actually run this program with debugging, okay, where it exits immediately after program completion. But notice here, I'm going to get it twice because it's disabled automatically. Okay, so in short, it shouldn't really matter if you're using the latest version of Visual Studio and the default settings, of course, whether you run with debugging or without debugging. All right, so just to illustrate the difference there. But of course, if you are by any chance using an older version of Visual Studio, you may still have to include that system pause statement if you are running with debugging. Okay, so I hope that clears that up there. Just before we finish up here and ask you guys to have a go at the remaining exercises, which hopefully you should get on okay with. I just wanted to draw your attention to the last exercise, because remember I said in the presentation that this time factor is going to play a part in your assignment for this module. So I thought it'd be a good idea that we practice this before finishing. Okay, so I just wanted to model that to you. And let me just tell you what, I can comment out this code because I'm not going to need it. Saves me having to type it in all the time. So let's just have a little reminder to myself. I'm going to use a block comment, and I also don't need system pause. So I'll just block that out. And then let's say exercise 9 here. All right, or perhaps if you're comfortable, you might want to delete it to save room. But I think, can you actually minimize? I think you can actually minimize comments. There you go. So that saves room there and saves you having to delete it. All right. So look out for that minimize and maximize for the comments there. All right. And let's just have a little indicator. I'm on exercise 9. Okay. And let's just do a bit of formatting here. Let's put these in. Okay, and if I go back to the slides, I think I'm going to have to include it's either ctime or time.h. I think it could be either. Let's try time.h. If I include that, time.h, time.h at the top there. Remember, that's an example of a preprocessor directive, a statement with a hash in front of it. We're going to be exploring that in more detail soon. But for now, just know that it's a way of including other classes, other library files. So you just want to include time.h if you're going to be attempting this time exercise. And then if you cast your eye to the code, we can have a go at actually putting this into practice. So we need to set up a variable to be able to store the time, the number of seconds that have passed. So it has to be in this format. That's underscore underscore time32 underscore t. And then in this given case, it's just going to be called raw time. Of course, in theory, it could be called anything, but just sticking close to the example here. And then we're going to want to set up a structure using the struct keyword, and then tm. I presume that's a time format for our struct. It's going to be called time info in this particular case. And struct technically is different to a class, even though you can have attributes of a struct. I think it's different from a class in that it can't have inheritance properties. So we can still create variables, or I guess they would still be called variables because object is a object-oriented term. So you might say this is a variable of a struct, but just to keep it in line with what it's expecting, we'll use struct rather than class. And then finally, we're just going to want to create a character buffer. I think this is going to be the formatting. So this is just going to allow us to convert to string. Essentially, string's character array. So it's just going to convert the system time information into string format so that we can easily view it. And then from there, let's start the process where, first of all, we have to pass the raw time, this variable, which currently doesn't have anything in it, to a time32 function. And you notice that we're actually going to be passing it by reference. Notice the ampersand there. Remember, we said that in the presentation. That passes the memory address of this variable, not the actual value of it. We're not passing by value, we're passing by reference. So therefore, we directly modify the value of this address, okay? Because you notice we're also not passing anything back to update this raw time, all right? So this allows us to directly modify it via the memory address, okay? So it's underscore time32, it's the function name, and then you will say ampersand, passing the memory address of raw time, the variable. I think that should populate it with the system time, the number of seconds that have passed since the 1st of January 1970, which is obviously going to be a very large number of seconds, but that should then populate it. And then we want to convert that to our struct, because remember the struct is going to hold some different attributes for the month, the day, the hour, the minute, the seconds, all kinds of other time-related categories. So this underscore local time 32 underscore s is going to be the function that we need to use, and time info is the destination, and then the other parameter we want to pass is the number of seconds. So basically convert the number of seconds into those categories. All right, this is a pretty handy method actually for interpreting this huge number of seconds that are going to be passed to it. So it's obviously very clever at dividing that up into the individual categories. And then finally, the last method we call is ASCII time underscore s, which will convert those number of categories into our character buffer. All right, so that we can then print that to screen. All right, so we're going to pass in the buffer. The size of it, we've allocated 32 elements, which should be enough. And then the reference to time info, the struct, okay, the different categories that we've got. All right, so then the final thing to do is just to print out that buffer. All right, so hopefully, if we've done this correctly, we should see the current time of running this. If we print the buffer to screen. Okay, let's give this a try. Let's see what we see. And there we go. We get the current time at the time of running this application. All right, so we've got lots of different categories here. We get the calendar day, get the calendar month, we get the actual day of the month, and then the hour in 24-hour time, minutes, seconds, and the year. All right, so lots of different categories there that you can refer to. And I think that is the next part of it. Yeah, actually displaying the individual values for hours, minutes, and seconds. So now that we've got it into the struct format, we should be able to refer to those individual categories. Show you how to do that. If you refer to time info, and then say dot, you should see a long list of different attributes that you can refer to. So if you say, what is it? We're looking for hours. So let's say TMR. Do a bit of manual formatting as well here. So I suppose the handy function of this is you can format in any way that you want to, but just to try and replicate the clock with the colon, let's say then minutes. So it's going to be TM min, and then one more for seconds. Time info. Seconds. All right, and then end the line. So if we run this again, we should see just those portions of the TM struct. And there we go. You'll notice that we've extracted those individual categories, the hour, minutes, and seconds from the full date and time structure. All right, and then I think the final thing is just to display the number of seconds. So if you were curious to know the colossal number of seconds that have passed since 1st of January 1970, I think you just have to refer to raw time. So if you just print that out to screen, you should see the huge number of seconds. And there we go. I'm not even going to attempt to work out what that is, but that's probably several, could even be a trillion or maybe several billion seconds that have passed since 1970, over 50 years ago. And thankfully, we don't have to interpret it. Thankfully, there's a function that can do that for us. All right, so there you go. Hopefully that gets you started with time. As I say, do keep this in the back of your minds because this is going to come into play later in the module. So do make sure you have a go at it and keep this code handy because it will definitely be useful later on. All right, so hope that demonstrates that. Give it a go yourselves and have a go at the remaining exercises. Hopefully you won't encounter too many problems. But of course, if you do, just shoot me an email. I'll be more than happy to take a look at it with you. All right, so give the rest a go and see how you get on.